Hello, today's topic is internal forces and beams, and this is part 2. In this part, I will show you how to draw internal force diagrams for simply supported beams, and how to do it quickly and efficiently without writing equations. Some professors require writing equations to draw internal force diagrams, so you need to make sure if those equations are necessary for you, or if you just have to draw the diagrams, and that's it. Without writing equations, the diagrams can be drawn much faster. The second example, a bit more interesting, more forces. We also have one concentrated force, 2 moments applied to the beam, and a distributed load. And 2 supports, a movable hinge support and a fixed hinge support. So we mark the reactions at the supports. One we already know, which is 0, meaning that the horizontal component is 0. And here, there will be the reaction Vd, and next to it will be the reaction V. And once we have that marked, we can take care of calculating those reactions. So as I mentioned earlier, first we will do moments either at point B or at point D to calculate one of those reactions right away. So I did it at point B. Now we will also calculate the resultant of the distributed load, which is 15 times 2, that is 30 and is in the middle. That is at a distance of 1 meter from this support on the left side. How much did I say, 30? And now the sum of moments at point B equals 0, so minus 10 times 2 plus 30 times 1. The moment is applied as counterclockwise, so minus 10 minus Vd times 4 and minus 15. From this it follows that Vd is equal to minus 3.75. So I have a negative reaction, which means that I assumed the direction incorrectly, so I will change the direction to the opposite. Just like before, and here I will make a plus. And from this point on, it looks like this. And we will write the next equation. The sum of projections on the y-axis equals 0, we have minus 10 plus Vb minus 30 minus 3.75 equals 0. From this, Vb equals 43.75 kN. And we can start drawing the diagrams. So here we go. First, the shear force diagram. We have a shear force applied here of 10 kN, so there is a jump of 10 downwards. Next, there is no applied shear force on the beam, so we will go linearly to the next point. Here we have the reaction Vb. It is 43.75 and pointing upward. So we move up by 43.75 from this minus 10, thus to 33.75. Then we have the distributed load. Its resultant value is 30 kN, so from the value of 3.75, we will move down by 30 according to the direction of this load. So, meaning from the negative side, linearly. We are under continuous load, which is up to a value of 30.75. 30.75 minus 30, linearly. So, here we have 3.75. Next, there is no shear force on the beam, so we move without change to the next point. Here is plus, here is plus. So what is the reaction Vb? 3.75. The graph goes down to 0. We know that it is okay. Next, we have no shear force, so in this part it is 0. And we have the shear force graph drawn. Now I will calculate the areas of the figures that have appeared here. So 10 times 2 is 20. Next I have a trapezoid. So a plus b times h over 2. So 33.75 plus 3.75 times 2 over 2, which is 37.5. 37.5. Here, we also see that the shear force graph does not cross to the other side under continuous load, so there will be no extremum on the moment graph. The area of this is 3.75 times 2, so 7.5. Now we draw the graph. So is there a moment applied here? No, we start from 0. Is there a moment applied here? Yes, 15. So here we start from 15. This moment arrow stretches the lower fibers, so the graph is on the side of the lower fibers. How else can we approach this? I look at it like this. This 15 would like to push the graph out here. And if it were in the other direction, that is right-handed, it would want to push the graph upwards. Okay, so this 15 makes the graph down here, that's for sure. From the first basic things we can write down. But let's calculate from the left side. Area 20, it is negative, so we move towards minus by 20. Graph Q was constant, so M is linear to a value of 20, minus. Then a parabola towards plus by a value of 37.5. So we move to the other side to 17.5. And along the way there is no extremum, so this graph will not look like that. It is simply a parabola, but it ends here. There is no value greater than the one at which this graph ends. Okay, let's say it looks like this. So what value are we at? 17.5. Well, it's not too pretty. Next by value. And somewhere here we also have a moment. Here is a moment of 10 kNm, so we have to be careful. Here, there will be a jump by the value of this moment. If a moment is applied to the beam, then on the moment graph, there is a jump by the value of this moment. It is left turning, so when we look from the left side, it is negative for us. Because when we cut from the left side, those are positive moments. And when we cut from the right side, those are positive moments. So that 10, when we look from the left side, is negative. So there will be a jump towards negative values. So we subtract that 10 because we are at a positive value. So we are moving to the value of 7.5 here. Here is 7.5, and from here now. Yes, good, good. And from this 7.5 now about the value of this area towards the positive. So we are at positive 7.5, and we need to move 7.5 back towards the positive. And here was a constant value, so we linearly. It is linear. 15, which is 7.5 plus 7.5. Next, here is no area, so linearly. At this 15, which is here on the other side. Without changing values. Plus and plus? Well, as I said, it is not very aesthetic, but I just wanted to show you what it looks like live, drawing such a graph without writing equations. Meaning, I will not show you the graph right away and talk about it, but I will draw it on the fly. I think it's easier to understand what is happening and why. So you see that even on such a difficult beam, drawing the graph is not terribly difficult. If we could just realize that it's wrong. Yes, drawing this graph from the left side. For example, we wouldn't end at the value that surely has to be at the end, which is 15. Then we would have miscalculated something earlier. Or for example, it should be 0 here, and it ends at some value, and there is no moment here. So there cannot be a moment at the end of the beam if it was not applied. Then we can know that we made a mistake. All right, and that's it for this example. So thank you for your attention. I hope I helped. If you have any questions or concerns, I invite you to ask questions and leave comments under the video. I also recommend other productions, encourage you to visit our social media, and of course to subscribe to this channel so you stay updated with new videos from EduPanda. In the meantime, thank you very much. Best regards, goodbye.